Hey there, Chris McCarthy here at SF State. Electromagnetic waves, light, consist of electric fields going up and down, increasing, decreasing, and magnetic fields increasing and decreasing at the same time. We can represent that in a simplified way by an electric field, E, whose vector points up and then down and then up and then down. Even simpler, I've got a wave right here. I use this wave to represent one electromagnetic wave. Now, when a second wave collides with this first wave, two interesting possible phenomena can happen. Here's the second wave. This wave might collide with the first wave in perfect sync. If so, it would look like this. The two waves are completely synchronized, and when they add together, their electric field vectors will make an even more powerful wave. That's called constructive interference. Constructive. On the other hand, this second wave could meet up with the first wave after some delay. Maybe it took a little longer for them to get to their meeting point, and this wave is a little bit behind. If so, it might be synchronized like this. In this case, the second wave is perfectly out of sync with the first wave, and as you can see, the up part of this wave matches with the down part of that wave, and when you add those two vectors, they will combine to form no wave. That's called destructive interference. If this is a light wave, you can actually have light canceling out light in this way. So whether we have constructive or destructive interference depends on how the waves line up, and that depends on the wavelength of the wave. We can draw the wavelength as the distance from peak to peak, like this, and label the wavelength with the Greek letter lambda, L lambda for length. If the offset between these two waves is 0, as shown here, then that's fine. They're in constructive interference. But if the offset is half a wavelength, this distance here, that's lambda over 2, then the interference will be destructive. You can also have an offset of one entire wavelength. Let's see that. Here is the first wave. I'm going to offset it by the entire length of one wave. If the offset is one whole wavelength, as you can see, it's synced back up again. We have, again, constructive interference. So whether this offset, which we will represent as delta L, is a half integer or an integer number of waves determines whether we have or not we have constructive interference. If delta L is 1 lambda, 2 lambda, 3 lambda, 3 waves exactly, then we have constructive interference. And if it's half a wavelength, lambda over 2 or 1/2 lambda, or 3/2 a wavelength, there's 1/2 and there's 3/2, well, that will create destructive interference also. Same with 5/2. So these are the conditions for destructive or constructive interference. The offset between the waves should either be 1, 2, 3, an integer number of wavelengths for constructive interference, or a half integer number of wavelengths for destructive interference. Now you might be wondering, what if it's not exactly any of those? Yeah, that's possible actually, and it's just neither constructive nor destructive interference. But it's when either constructive or destructive interference happens that the interesting phenomena of interference show up. So that's what we focus on mostly.